Welcome to Homework Lib.
Coulomb's law. In order to figure out the electric field of a thin rod, and we're finding the electric field off to the right of that rod, which is lying along the x-axis. So in order to use Coulomb's law, form of the electric field, we really want to think about that rod being broken up into tiny chunks of charge. We'll call them dq. And since we have a linear rod, we are going to write dq as a product of linear charge density, where lambda is if it's uniform, it's the total charge on the rod divided by its length, which they are calling little l. But what you're doing with Coulomb's law is you're starting with the form for the electric field magnitude. And here we're going to assume that the electric field is pointing entirely along the x direction because of symmetry. That is, there is symmetry going all the way around the wire such that the y and z components should cancel each other out. So what we're really finding is the x component of the electric field. And if we do that and use Coulomb's law, that should be kq total over x separation, but we'll call it r squared. It'll be a separation in x squared, which will work out. But usually what you do to break this up is you write the electric field as a sum of a lot of electric fields due to little tiny chunks of charge. So your q total becomes dq. And here dq is lambda times some linear differential, which is going to be along the x direction, because we are going to integrate over the source and use x as a way to count which source charge, which little infinitesimal source charge we're looking at. So we can rewrite our integral this way. And r, what the r is in that formula is it is the separation between our observation point, which I'll just call x, minus our source point. Now those are all negative values, but we'll just call those x source. And it's the magnitude of that. Now, we don't worry too much about the magnitude because we're going to square the quantity, so we don't have to worry about negative values getting us messed up. And the dx, okay, so it's important to realize the observation point is fixed, and we're not letting that move around in the integral. It's the source point that's moving around. And so we have a fairly simple relationship for a tiny differential part of the EX field, X component of the field. Now, this is where we want to integrate over the source points. And what you're really saying is that the electric field, you can use superposition. The superposition idea, that electric field from many, many points is just the sum of all the little electric fields added up. So we're going to integrate that on both sides. And yeah, that is an exact differential on the electric field side. And we'll pull out our electric constant and our lambda. And then our integral over x is going to go from minus L, the x coordinate where the wire starts, all the way up to 0 where it ends, and then dx source over, whoops, talking so much I forgot the x squared idea. Yes, the denominator is squared. Okay, and you can do that integral using a substitution, such as u is x minus x source, and du with minus front is dx source. So I'll just do that integral carefully to make sure I have it right. And then I have du times u to the minus 2. I know I'm being a little sloppy the way I write my integral. Maybe I should be a little bit more conventional. Usually they like the du holding the function in. And I've included the negative sign. So that's u to the minus 2 du. What is the lower limit? It is x minus L, x plus L, sorry. And the upper limit is just x. Okay, and that's a fairly easy integral. It's just u to the minus 1 with a negative sign that cancels the one out in front. And we can mess around with this a little algebraically. I don't know how much people need to do this. But we can get common denominator and also put in for the lambda. Let's see, that would be x plus L minus x all over x times x plus L. And yes, there are some pretty nice things that will cancel. Okay, and what's nice is we can see the final answer definitely varies as a 1 over a distance squared. The other thing to realize is that there are things you don't want to do with that formula. So notice that it blows up at x equals to 0. And that is always true. An electric field that's sitting right on top of a charge source will be infinite, more or less, if you use Coulomb's law. So don't use that point, but it is valid for just about any other point on the axis. And also notice if the x is much, much greater than L, so you're really, really, really far away from the rod, then the EX actually looks like an electric field for a point charge. It goes strictly as a 1 over distance squared. So both of those are some things to recognize about that relationship.